G'day chemistry students. In this video we're going to be covering dot points 3.2, point 4 and 6 and we're going to be focusing on the structure of redox reactions. Let's get into it. Now for most chemical reactions, almost all of the reactions that you look at within the scope of this course, pretty much all of them can be defined as a redox reaction. And in these chemical reactions what we see is a transfer of electrons. One substance will oxidize, meaning that there is a loss of electrons, and one substance will reduce, meaning that there is a gain. Now, redox can be summarized by this mnemonic here, oil rig, where the part that is oxidizing, that where oxidation is happening, represents a loss of electrons, and the part that's being called reduction is a gain of electrons. And you'll note that the term redox is a merging of the terms reduction and oxidation. So in this case, in this example that we've got here, X is oxidized by Y, which means that X is losing electrons. It's giving it away to Y. Another way of saying that something is oxidizing is by calling it a reducing agent. So if X is a reducing agent, what that means is it's capable of causing reduction in another substance. And X increases in oxidation number. Now we'll talk about oxidation number in the next slide. And for reduction, we have a gain of electrons. In this case, Y is reduced by X. Y gains electrons in this one, and Y is an oxidizing agent, which means that it can cause oxidation in another substance. Also, Y decreases in oxidation number in this example, but again, we'll talk about oxidation number in the next slide. Keep in mind, and this can be a little bit confusing when we start to look at redox reactions, we're looking at a reduction of charge, not a reduction in the number of electrons. So you might go, reduction, why are we gaining electrons? That's a little bit backwards. Think about it in terms of charge. So for example, if Y had a charge of 0 and it gains an electron, it will drop its charge down to 1, meaning that there has been overall a reduction in charge. Moving on, let's start looking at oxidation state, which may also be called oxidation number. Now, for most examples, it's pretty much the same as the valence concept that we were looking at earlier on in this topic. It's the charge that exists on particular atoms. Now, this works really well for ionic substances, less so for other substances that may be covalent, for example. But in general, oxidation state is a hypothetical charge an atom would have if all bonds to atoms of different elements were treated as ionic. And so really, it's not an actual charge that things have, that atoms have within a molecule, but it helps to explain the changes that may occur in a redox process, because it helps us keep account of all the electrons and where they're moving to. So just in general, when we're looking at redox reactions and we're looking at a molecule itself that could be ionic or covalent, it's really important to remember that those starting molecules have a neutral charge. So as an example, iron chloride here will have a beginning charge that is neutral. The whole idea is that the charges of the two components, iron and chlorine, will balance each other out. And that goes the same for all of these other examples too, including covalent substances like hydrogen bromide. We are assuming that the charge is neutral at the beginning and that the charges of both parts, or the oxidation number of both parts, balance each other out. Now, just in general, there are some rules that we can sort of follow. These rules aren't going to be particularly important for this topic, but I just wanted to show you some examples to show you the idea that oxidation states can change, and we'll further explore this in our lessons together. But in terms of assessments, etc., I wouldn't expect a lot of this concept to crop up. It really just helps to explain some of the big picture concepts that we're looking at in this topic. So as an example, when we look at group 1 and group 2, so the elements that are in our S block, they always have a charge of +1 and +2. For hydrogen, they always have a charge of +1 unless they are bonding to a metal, in which case they're the things that gain electrons. But usually they try and give their electron away and get a charge of +1. Fluorine always has a charge of -1. Oxygen almost always has a charge of -2. That can be changed when it's bonded to a fluorine as well. And then the only other exception is when it forms hydrogen peroxide, in which case it has a charge of -1. And then again, most of the time, chlorine has a charge of -1, but there are some exceptions to the rule. So with these rules, you can look at most substances and figure out the oxidation states of all of the components, all of the elements present in different molecules. So for example, if I have iron chloride here and it's FeCl3, I have 3 oxidation states for chlorine that are -1, and that's by our rule that's here, which means that if iron chloride is neutral, and we are assuming that it is, by the rule that's up here, then that would mean that iron would have a charge of +3. You can sort of go through the others and see the same thing. This one here is probably one of the more interesting ones. It's OSO4, I believe. OS is osmium. I'm doing that from memory. Check the periodic table. If I'm wrong, let me know. But the oxidation state of oxygen is always -2, with the exception not being present in this case. And so if you have 4 charges or 4 oxidation states of -2, they all add up together and would only be balanced out by a charge of +8. So you can see those examples there, and the others all balance out in the same way too. So what I want to look at now is an example of a redox reaction. We'll look at some more complicated ones and start to branch out from something as simple as this, but this really helps to show what's actually happening in a redox process. Now, this has come from a video by a gentleman called Tyler DeWitt. He has lots of videos on chemistry. They're all quite helpful. This video that he had on redox reactions is super helpful and goes into some of these redox concepts in a little bit more detail and sort of elaborates on some of the topics that I'm talking about now. But when we start looking at one of these examples here I have sodium and chlorine forming sodium chloride, and in this reaction, sodium metal starts with an oxidation state of 0. It's just the metal by itself and is completely neutral. And chlorine gas also has an oxidation state of 0 as well. But when they react, what can end up happening is when you form NaCl, there is a transfer of electrons, and that's sort of assisted in visualizing down the bottom here when we look at an example using Lewis dot structures. So in this case, you have a sodium giving away its electron to chlorine, and that ends up forming a sodium ion and a chlorine ion, which when I word it that way may seem a little bit more familiar to you. But in this example up here, we have 2 atoms to begin with, which have an oxidation number of 0, which matches its Lewis structures down the bottom. And when we transfer an electron from sodium to chlorine, we end up having 2 charged particles, charges matching their oxidation numbers. Now, what you'll notice is that there's actually 2 processes happening sort of simultaneously. There's an oxidation process in which the sodium is giving away its electron. It's turning into a positive ion and giving away its electron. And there's also a reduction process where that electron is being taken up by the chlorine, forming a negative ion. Now, if oxidation's occurring, there's electrons being given away. It's really important to realize that there is also always going to be a reduction happening at the same time. If an electron is being given away, it needs to be given somewhere and picked up by another substance. Thank you very much, everyone. Now, in the next video, we're going to be looking at an application of redox, which is a galvanic cell, which can be used actually to produce electricity chemically. But until then, have a good one.